In this session, we're discussing about strain energy. Strain energy within a system like this, where we have a uniform load simply supported by two springs, right? So, in order to solve a situation like this, you divide the system into two sections. One section which involves the UDL, which is the uniformly distributed load, right? Uniformly distributed load, and the springs themselves, right? So in these springs we're given the spring constant, K for each spring. In this case they are similar, and we're also given the length of the beam, and we're given the uniform load, the load density, which is load per unit length, which is 10 kilonewtons per meter, right? So we have to determine the strain energy, the total strain energy within this system, right? So the first thing we do is, let's work with the first scenario I said, which is the beam itself, right? So the beam is experiencing a certain load, W, which is equal to 10 kilonewtons, right? So let's work the system together, okay, let's redraw the system. We assume that we take this thing as if it's simply supported, right? So the weight that this beam is going to experience, the reaction force that this beam is going to experience, let's call this RL and this RR, right? So we need to determine these reaction forces, right? So we know that in a UDL, the total weight that this beam is going to exert is equal to the weight density, which is W, times the length of the beam, L, right? And we know that the reaction force, if this thing is uniform, then the reaction forces at these two edges, RL is equal to RR, right? So how do we determine this? We use that equation of the sum of forces within the y-axis, which is summation of forces in the y is equal to 0, since this thing is statically determinate, which is, it is in equilibrium, right? So is equal to WL, which is the force that is going down, is acting at this point, WL, then WL minus, so in this case we know that RL and RR are the same. We can take any of the two, which, let me just take RL by 2, since they are 2, right, going upwards. So in this case we can determine RL. So RL is equal to omega L over 2. All right. Okay. So now let's find the bending moment. Remember, to find the maximum strain energy, the strain energy within this UDL, the equation goes like this: strain energy is equal to integral from 0 to L of m squared over 2I E dx, right? So I m being the bending moment, I being the second moment of area, and E being the Young's modulus, right? So now we are in the process of determining the value of the bending moment. So the bending moment, how do you determine the value of the bending moment? Let's take a position X from one edge of the beam. Let's call this X, right? So we assume that we are pivoting the beam at this X. We need to find the bending moment of the beam at this point. So to find the bending moment, we have okay, before we do that, let's allocate our directions. Let's call the clockwise moment as positive and the anti-clockwise moment is negative, right? So here, looking at this position, we sectioned our beam, and looking at this position, we are looking for the bending moment in this side, the total bending moment. So the total bending moment becomes M is equal to, if we look at this, we have one clockwise, which is RL times the distance x, right, minus we have this part of the UDL, which is omega x, right? But you see that omega x is not acting at this point, it is acting at the center of it, which is a distance x over 2 from the point of pivoting, right? So this would be the resultant bending moment. But we know that RL, from our calculation, RL is omega L over 2. So it's omega L over 2 x minus omega x over 2. So this equation simplifies to omega L x over 2 minus omega x squared over 2, right? Okay, we can further simplify this to omega x over 2 L minus x, right? So this is our bending moment. So we can position, now we need to find the strain energy, right? So we can square this. This equation becomes m squared is equal to omega squared x squared over 4 L minus x. Now we just take this and substitute it in the equation of strain energy, where U is equal to integral from 0 to L of omega squared x squared over 8 IE bracket, this one we expand it, sorry, it's supposed to be squared here, we expand it, L squared, right, minus 2LX plus x squared dx. So we factor out the constants now, right? Factor out the constants. Again, sorry, you need to shift this to another page. Let me just rewrite this equation on the other page. So remember, bending moment m is equal to integral from 0 to L of omega squared, right, over 8 L over 8 IE, sorry, times x squared bracket L squared minus 2L x plus x squared dx, right? So if I said we factor out the constants, which becomes omega squared over 8 IE, right? So in the integral sign, we're left with, we can multiply this by the y equation, which becomes x squared L squared minus 2 L x to the 3, right, plus x to the 4, right, dx, right? We can integrate this. Our equation becomes L squared over 8 IE full bracket, and we're remaining with L to the 5 over 3 minus 2L to the 5 over 4 plus x to the 5 over 5, 0 to L, right? Our equation simplifies to omega squared L to the 5 over 240 IE. So this is the total strain energy that is found within the beam, right? So the value of I and the value of E will be given depending on the cross section of the beam, right? If we are given a beam with a cross section like rectangular cross section where you have B and D, remember that I is equal to BD cubed over 12. If it's a circular cross section of the beam, then you know that I is equal to pi d to the 4 over 64, right? And the value of E is given as Young's modulus, right? So this is the total, strain energy, right? Oh, sorry, this is this is total strain energy within a bending moment of a UDL, right? So in this case, in our equation, let me just flip back to our here. I forgot to mention that we are given strain energy, Young's modulus as 200 gigapascals, right? And we're also given the cross section of the beam, which is like this. So B was 4 centimeters, and this one was 5 centimeters, right? So from this we can calculate our I and the value of E is given. So E is given our I, so our I becomes BD cubed over 12, which is equal to, what is the value of B? The value of B is 4 centimeters, which is 4 times 10 power minus 2, right? Times, what is the value of D? 5 centimeters, 5 times 10 power minus 2 cubed over 12. So we just punch these values in the calculator. This becomes 4 expand minus 2 times bracket 5 expand minus 2 cubed over 12, right? So this is the value that we're getting, which is 4.167 times 10 power minus 7 meter to the power 4, right? So now the value of E, we have it. So to find the total strain energy within our beam is equal to omega. Remember omega, we have it, which is 10 here, right? Our omega is 10 and our length is 6 meters. We just substitute the values as they are. So this becomes 10 squared times 6 to the power 5 over 240 times our I, which is 4.167 times 10 power minus 7 times E is 200 times 10 power to the power 9. Just punch these things into the calculator. It becomes 0. Okay, the value of it's 10. Actually, I'm sorry, it's 10 kilo newton per meter, right? So this value, it's actually 10k squared, right? So this becomes 10 times 10 to the 3 squared times 6 to the power 5 over 240 times 4.167 times 10 power minus 7 times 200 times 10 to the power 9. Okay, you can punch this into the calculator, which becomes 10. You can just punch this into the calculator. 10 expand 3 squared times 6 to the power 5 over 240 times 4.167 expand minus 7 times 200 expand 9. Okay, so this is the value we're getting for total strain energy. which is 38.89 kilojoules. So this is the total strain energy stored within the beam, right? Moving on to the second section, which is the springs, right? Let me just go to the fresh page. So we're saying that there's a beam which is supported by springs, right? The springs with a spring constant of 8. We say it's 8 meganewton per meter. 8 meganewton per meter, right? So we know the force that is being applied within this spring, right? To find the total strain energy of a spring, this is the equation for finding total energy of a spring. Is equal to total strain energy is equal to half kx squared. K being the spring constant and x being the deflection that is taking place in the spring. So to find the deflection, here the K we have it, but we need the deflection. That's the thing that we don't have. To find the deflection, remember F that is applied on the spring is equal to Kx, x being the deflection that we're looking for, right? X being the deflection that we're looking for. So how do we find the deflection? The deflection x is equal to F that is being applied on the spring over K. But you know the F that is being applied on the spring, remember that this is a UDL and it's applying a certain load. The load that is applied in this direction is WL, right? And you know that we have calculated the load that is being applied here, which is WL over 2. So we know that the force equal to WL over 2. Can then substitute this. X becomes WL over 2K, right? So this is our X. So to find strain energy is equal to half K times WL over 2K squared, right? So we can then just simplify this. This becomes K dot omega squared L squared over, this becomes 4, this becomes 8 K squared. The K goes, this goes, so this becomes omega squared L squared over 8K, right? So this is the total strain energy that is obtained within our spring. We can then substitute our values. This total strain energy becomes, within the spring becomes omega, remember omega it's 10 kilonewton, 10 times 10 to the power 3 squared times L squared, which is 6 squared over 8 times K, remember K is 8 meganewton per meter, which is 8 megapascals. It becomes 8 times 10 to the 6, right? 8 times 10 to the 6. So you can then substitute this, just put them into the calculator. Sorry, so 10 expand 3 squared times 6 squared over 8 times 8 expand 6. So we get 56.25 joules. So this is strain energy within the spring. So the total strain energy becomes UT energy within the beam plus energy within the springs, which is equal to 38.89 times 10 to the 3 joules plus 56.25, which is equal to 38.89 expand 3 which is 38.95 kilojoules. This is our total strain energy. Thank you.